All right, so um, we'll start another topic, which is dynamics. Like the previous topic we treated, which is kinematics. Kinematics is the study of motion without considering the force responsible for the motion. Here in dynamics, we'll study motion with respect to the force responsible for the motion of the object. So under dynamics, we'll look at force, mass, and weight, Newton's laws of motion. So like we said before, motion is a change in position of an object over time. Now, for any object to move from one position to the other, a force is required. So the force applied on the object changes the position of the object from one place to the other. So what is a force? A force is a push or a pull on an object that causes it to change velocity or to accelerate. A pull on an object or a push on an object that causes the object to accelerate, to move from one position to the other. That is a force. Now, a force is a vector quantity. It has both magnitude and direction. It is measured in the SI unit of Newton and represented by a symbol F. There are two types of forces. We have the contact and non-contact forces. By contact force, we mean that there is physical interaction between the object that is set to move and the force applied to make the object to move. So force that exists during physical interaction or physical contact is referred to as contact force. And example of contact forces are tension. Tension is when you apply a force by pulling an object using a cable or a rope or whatever means to pull or an object to move. That's the force applied in this manner is tension force. Then frictional force is any force that opposes the motion of an object. An object is moving forward, there is a reaction force that is causing the object to slow down because the force is acting in opposite direction to the direct applied force. So that tends to slow down the motion of the object. That is friction. Friction opposes motion. And applied force, of course, the applied force is the force we apply to make an object move from one position to the other. The second type of force is non-contact force. So the force that exists with no physical contact is called non-contact force. So all field forces are in this category. For instance, if I place a magnet and a piece of metal close to the magnet, not in contact, we will know that the magnet will attract the metal to itself. And that attraction itself is a force. That is force of attraction. The same thing happens if I place charges beside themselves. If the two charges are of the same kind, there will be a pushback. That is force of repulsion. If they have opposite charges, they will come together. That is force of attraction. So the same thing happens to gravitational field. So all field forces are non-contact forces. Now, mass and weight. Mass is the quantity of matter possessed by a body, whereas weight is the gravitational force by which the earth attracts object towards itself. Mass is a scalar quantity. It has only magnitude. Weight is a vector quantity and has both magnitude and direction. The unit of mass is kilogram, while the unit of weight is Newton. Mass does not change with position. That is, if I carry a piece of object, the mass of that object will remain the same wherever I carry that object to. Whereas if I say I want to measure the weight of that object, the weight will change with position. The weight changes because weight is mass times acceleration due to gravity. Gravity changes with position. Within the surface of the earth, or near the surface of the earth, gravity is constant with a value 9.8 meters per second square. But as you ascend into the altitude, the gravity begins to vary. For instance, in other planets, in Mars, in Moon, in Jupiter, Saturn, and so on, the gravity there is different from the gravity on the surface of the Earth. However, the mass of the object remains the same, but because gravity changes, the weight of the object will also change. Mass is measured by using physical balance, beam balance, or electronic balance, whereas weight is measured by a spring balance. Now, we move on to first law of motion, Newton's first law. Newton's first law is taken from inertia. Inertia is the tendency of a body to remain at rest, to resist being accelerated. That is, when an object is at rest and does not want to move, that is inertia. The tendency of a body to remain where it is and resist move acceleration, that is inertia. So from this concept, Newton came up with his first law and states that an object at rest remain at rest, or in motion remain in motion on a straight line at constant speed unless acted upon by an external force. So if the object is at rest, it wants to remain at rest, and if it's in motion, it does so at constant speed on a straight line unless acted upon by an external force, which means that according to the first law, the forces acting on an object is balanced. The forces acting on an object is balanced. So the sum of the forces acting horizontally on an object is equal to 0. And the sum of the forces acting on an object vertically is equal to 0. Here we have free body diagram with respect to first law. A free body diagram is a pictorial representation of all the forces acting on an object with complete label. So looking at the diagram, we have a force, a body or a block or an object laid on a horizontal plane. The forces acting on that object are 4 of them. We have the normal force, which is pointing upward. The normal force pointing upward. And these normal forces as a result of the force exerted by the horizontal table or plane. We also have the weight force pointing downward. Then we have the tension force, because this object is being pulled with the help of a rope. So the tension force is acting to the right. And when the first object is moving towards the right, there will be an opposing force, which is the frictional force to the left. Now, according to the first law, Newton's first law, the forces acting or the force acting upward is balanced by the force acting downward. And the force or the tension acting to the right is balanced by the tension acting to the frictional force acting to the left. So we can write that T is equal to FF, that is horizontal force, T is equal to FF, and we can also write that Fn is equal to Fg. This is vertical force because the object is at equilibrium. So Fg is the weight, it's also mg, always acts downward from the center. Fn is the normal force, is surface force always drawn perpendicular to the surface. Tension T or Ft, force in rope and always drawn away from the object. Frictional force is force that opposes the motion of the object. So let's look at this example. A 10 kg box is being pulled across the table to the right at a constant speed with a force of 50 Newton. Calculate the force of friction. A. B. Calculate the normal force. Now, to solve this kind of problem, you have to understand the question. For the fact that it is stated in the question that the object is going pulled towards the right at a constant speed. Remember that Newton's first law states that an object at rest remains at rest or in motion on a straight line at constant speed, which means the object is not accelerating. If the object is not accelerating, the forces acting on the object are all in equilibrium. So, which means this is problem with first law, or first law, Newton's first law problem. So by Newton's first law problem, we know that the horizontal forces are balanced. The force on the right is equal to the force on the left. The vertical forces are also balanced. The force upward is equal to the force downward. So now we are asked to find the frictional force. The frictional force is the force on the left. This is balanced by the force on the right. The applied force is 50, which is the force on the right, that is pushing or pulling the box across the table to the right. So FA is equal to FF, and since FA is 50 and is equal to FF, FF will be 50 as well. Then the vertical forces, two of them, the force upward is equal to the force downward. We are asked to find the force upward. And the force downward is mg, which is 10 times 9.8, that is 98. So our Fn is equal to 98, our Ff is equal to 50. Suppose now from the same problem, if this time instead of the box is being pulled straight this way, but this time is being pulled at an angle. It's being pulled at an angle, and we are at the angle is 30 degrees. And we are asked to find the frictional and normal force. So to solve this, we have to resolve this to vertical and horizontal component. The vertical component will be 50 or FA, this FA. So the vertical component will be FA sine theta, while horizontal component will be FA cos theta. So what is FA? FA is the 50 Newton force that is applied resultantly to pull the object or the box at 30 degrees. So that will be 50 times sine 30 degrees. 50 times sine 30 degrees. Why this is horizontally, we have 50 times cos 30 degrees. So we are asked to find frictional force. Remember, this is first law, Newton's first law. The force on the right is equal to the force on the left because it is an equilibrium problem. The forces are balanced. So what is the force on the right? The force on the right is 50 sine 30. So the force on the left is frictional force. So the frictional force is equal to 50 sine 30 degrees, which is 43.3. 43.3 Newton. And then coming to the normal force, this time we see that we have normal force going up. We have the vertical component of the force applied going up, and we have the weight force going up. There are three forces. Two forces are going up, so we add the two forces going up is balanced by the one force coming down. So this upward force is equal to the downward force. We are asked to find the normal force. So we write an equation for that, which is Fn plus Ay is equal to mg. Fn plus Ay is equal to, that is this. Fn plus Ay is equal to mg. We are asked to find Fn. So we move Fay across the quality sign, and we have Fn is equal to mg minus Fay. So mg is, m is 10, g is 9.8, Fay is 50 sine theta. So if we substitute and simplify, our answer is 50 Newton. Now move on to second law. The first law says, unless acted by an external force. That is the conclusion of first law. Unless, so the object will remain at rest. If it's at rest, and an external force come upon it and act on it, it will no longer be at rest. It will begin to accelerate. If the another thing is, if the object is moving on a straight line at constant speed, and then an obstruction comes on its way, the object will change direction and begin to accelerate. That is external force acting on it. So when an external force acts on it, it will no longer remain at rest, or it will no longer be at constant speed. It will begin to accelerate. So if it accelerates, our F will no longer, some of the F sum of F as we have it in first law will no longer be 0, but equal to the mass of the object and the acceleration. So this sum of the F, we can also say that F net is equal to MA. F net is equal to MA. That is sum of the forces acting on the object is equal to MA. It's no longer equal to 0. So this, according to Newton's second law, it states that as the time rate of change of linear momentum is directly proportional to the applied resultant force, and the momentum change takes place in the direction of the force. So F is equal to MU. Remember that in previous class, we showed that A is equal to change in velocity over t. So if we substitute this into F is equal to MA, we are going to have this expression. That is F is equal to change in momentum over time. So that is where that statement came from. The time rate of change of linear momentum is directly proportional to the applied force, applied resultant force, and the momentum change takes place in the direction of the force. So now, from the previous slide, we saw that F is equal to mv minus mu over t. So if I So if I move t across to the F side, I will have Ft is equal to mv minus mu. So Ft is called impulse, while mv is called momentum. So momentum is the product of a body mass and its velocity, while impulse is a product of the force and time with which force acts on a body. So here is an example. Here is an example. We have A 10-gram box is being pulled across the table to the right by a rope with an applied force of 50 Newton. Calculate the acceleration of the box if a 12 Newton frictional force acts upon it. Yes. So this question is very close or similar to the previous one we solved. However, the previous one, there was a phrase there, constant speed. The constant speed, there made the problem to become Newton's first law problem. But here, there is no constant speed, and the object is accelerating. So since the object is accelerating, it is a second law problem. So for a second law, we start with writing the formula, which is F net. F net is equal to NA. F net is equal to NA. So what is F net? F net is the sum of the forces acting on the object, horizontally or perpendicular. Horizontally, we have two forces, the frictional force and the applied force. Now, these two forces are against one another. They're in opposite direction. So the resultant force, or the F net, will be the applied force minus the frictional force. And you will ask, why not the frictional force minus the applied force? Now, when you are finding the resultant of the force or the net force, always subtract the smaller force from the greater force, because the object is moving in the direction of the greater force. So since the object is moving in the direction of the greater force, it means that that is the positive direction. So the applied force minus the frictional force. The applied force is 50, the frictional force is 12. And the mass of the object is 10. So if we substitute these parameters to find the acceleration, we have acceleration to be 3.8. So 50 minus 12 over 10 is equal to A. 50 minus 12 is 38. 38 divided by 10 is equal to 3.8. So the acceleration is 3.8 meter per second. Three point eight meter per second. So let's look at this example as well. A mass M1 is 3 kg resting on a frictionless horizontal table. It's connected to a cable that passes over a pulley and then is fastened to a hanging mass. M2 equals 11 kg, as shown below. Find the acceleration of each mass and the tension in the cable. Now, find the acceleration of each mass. Don't be confused that you are asked to find the acceleration of each mass. However, the question is not asking you to find the acceleration of this separately from this. Of course, the two masses or the two objects are tied together, linked together by a cord. So the rate at which one is moving is the rate at which the other will move. So it's the same acceleration that we are going to find, a single acceleration. So our starting point is the first expression, which is F net is equal to MA. MA. Now, if we put our attention on the first mass or on the second mass here, the object is going down, which means, and there is a tension there are two forces acting on this block. One force is the weight force going down, while the second force is the tension force going up. So our net force, F net, sum of the forces acting on the object, will be the smaller force minus, or the greater force minus the smaller force, subtracting the smaller force from the greater force. How do we know which one is the greater force? The direction of the object shows where the greater force lies. So since the object is coming down, M2G is the greater force. So M2G minus T, tension, is the smaller force. M2G minus tension will give us MA. So that is how we got this first expression. M2G minus T, M2G minus T is equal to MA. This MA is this MA here. But because we are dealing with the second mass, so that is why the nomenclature is M2G minus T is equal to M2A. So take note of that. Now, for the first mass, coming to this first mass, the system, according to the question, is frictionless. So there is no frictional force along this direction, which implies that we have only one force. The F net will be only the tension force. So the tension force is equal to MA, and our MA has to do with the first mass. So T is equal to M1A. Now, having said that, we have two equations now. Equation 1 and equation 2. The T's are the same because the T here and the T here are the same because of this pulley, frictionless pulley. This is a simple cord that crosses from here to this other side. So we can substitute by moving this T is equal to M1A into this first equation. So when we do that, we will have this expression, which is M2G minus M1A is equal to M2A. Now, we have A here common. So we move this expression to the right-hand side. When we do that, we have M2, we will have this equation, which is M2G is equal to M2A plus M1A. Since A is common here, we bring A out of a bracket and put M2 plus M2 in a bracket. And since we are looking for A, which is the acceleration, we can simply divide M2G by M1 plus M2. That will give us A. Now we can substitute the parameters, which is M1, M2 is 11, G is 9.8. M1 is 11, M1 is 3, M2 is 11. So if we simplify this, our A is 7.7 meter per second square. Now, the next question says tension. Tension is M1A. So since our A is 7.7, our M1 is 3. So our tension will be 3 times 7.7, which is 23.1 Newton. So that is our tension. So now friction. Friction is the force that opposes motion between any surfaces that are in contact. When two surfaces are in contact and they are in motion, the friction will they will oppose one another. Frictional force is a force that opposes the motion of objects. We have two types of friction. We have static and kinetic friction. Static friction is a friction that keeps an object at rest and prevents it from moving, while kinetic friction is a friction that acts during the motion of an object and is represented mathematically as this. F, frictional force, is directly proportional to the normal force. And then the static frictional force is equal to the coefficient of frictional force times normal force. Kinetic frictional force is equal to the coefficient of kinetic frictional force times normal force. So we are going to stop the class here. Hopefully tomorrow, if there is time, when I come back in the evening, I can continue with this class so that we may not finish this topic this week. So if we are not able to, wherever we stop tomorrow, possibly we'll continue from there next week.